Road heavy transport in the European Union is a critical point. The amount of energy required and its environmental impact affects the climatic equilibrium, the healthy life, the ecology stability, etc. An analysis of the system and the role of the energy storage open the door to the understanding of the system and targeting the adequate and possible options to break the climatic drive. The role of hybrid energy storage systems could contribute to diminish the energy consumption. Opening a question. Can hybrid energy storage systems contribute to efficiency and safety and diminish the environmental impact? The roads network of Europe is very dense and allows high connectivity. It supports the concept of unity of the European Union market. Along 2023, the road network of the European Union supported the traffic of 13 billion tons and 2,000 billions of tons kilometer. Considering only food and tobacco, the freight accounted 300 billion tons per kilometer. The amount of traffic along the road network in the European Union is well reflected by two parameters: the global weight of the freight and the road distance between the origin and the destination. Two parameters are used in describing well the global movement: the weight in tons and the product of the weight and the distance in tons per kilometer. In the graphs, it is shown the evolution from 2000 to 2021 of the weight, achieving a level of more than 1.2 gigatons, and the weight per distance parameters achieving 700 billion tons per kilometer. The traffic of goods along Europe requires several types of trucks accordingly with the distance and the weight of the transport. The table includes the distribution by countries. Two groups can be considered: vehicles for short and medium distance and load for 9 to 20 tons, for short and medium distance and load. It includes distribution of merchandise. Vehicles for large distance and load from 20 tons to 30 tons until a maximum of 40 tons, habitually for long-range travels. The statistics show that the second sector represents an 80% of the total tons kilometer of the float. The rightmost categories in the table amounts a 44% of the global freight, achieving 800 gigatons kilometer. The category of trucks between 20 and 25 tons transport a 36%, with 670 gigatons per kilometer. These numbers show the colossal freight traffic along the 27 countries of the European Union. From 8 in the morning, the traffic towards France border at 140 kilometers starts the saturation of the highways and roads each working day. 1,000 large freight trucks pass to France every working day through the AP7. It is difficult to count the number of 5-axle trucks in the lanes of the highway. Where is coming from the energy? According to European Union statistics, gas oil and diesel oil, dark blue, is the most used, covering nearly 70% of the total energy demand, followed by gasoline and other as fuel and renewables, electricity, and liquefied petroleum gases that not contribute significantly. Looking at the rightmost graph, we can see the line just up to the year 2022, corresponding to road transport. It is clear the dominance of the road transport. The consumption achieves 11,000 petajoule. Water transporting through rivers, channels, and sea and air transport does not achieve a fifth of the consumption of the road transport. Railway transportation does not has relevance. From this graph, we should consider that the road transport is largely more active than the other options. Why the large difference with rail transport? In the leftmost map, we can see the highly measured net of highways and roads along the European Union. The flux of trucks depends on the kind of roads, being 22,000 trucks per year in the less used roads, and achieving 10,612,000 trucks per year in the highways. The flexibility in the selection of routes and the infrastructure supporting the network is probably the preference for road transport. These huge numbers suggest transferring 30% of the flux to railways. It could diminish the energy needs. At the rightmost graph, it is shown the railway's freight network. It is planned to increase the traffic, including the 30% of the road traffic. From the energy point of view, the rail freight has some advantages with respect to road. The energy efficiency of the rail freight transport is 24 grams of greenhouse gases per ton of freight and kilometer of travel. It is significantly cleaner than the road freight, just a fifth of the emission in the roads. Also, electrical mobility is dominant in rail freight. Some limits affect the design of the expedition through mountain regions where the track slope cannot exceed the 1.5%, amount that in the roads could be much larger. The geography of the European Union includes several chains of mountains that affect the travel of large freight expeditions. The analysis of the road profile allows to evaluate the increase of energy consumption. The satellite observation allows the knowledge of the road profile for the selected track. In the case of this first map, we can observe the freight expedition between two seas, the Mediterranean Sea and the Cantabric Sea, to shorten the ship expedition from Barcelona to Bilbao ports. There are two mountains regions with height 600 meters. From the profile below the map, we can see several ramping up sections and some ramping down sections. The total section up supposes a height gain equivalent to 8 kilometers and a depth of 8 kilometers also. Distances in each section are 310 kilometers going up and 306 going down. The average ramping up slope is 2.61% and 2.65% going down. This ramping showed an extra cost of energy. A large track is not considered, just a track from Barcelona to Wien. In this case, the ramping up sections supposed 37 kilometers and 37 kilometers also when ramping down with an average slope of 4% when going up and minus 4% when going down, with ramp length of 913 kilometers when ascending and 922 kilometers when descending. Each change of height involves a change of potential energy, as it is shown in the picture. A 40 tons track is ramping up 45 meters and down minus 30 meters. The change of gravitational energy supposes 1764 megajoule that should be supplied by the engine of the track, and minus 1176 megajoule when going down. This usually is lost by braking to avoid an excessive increase of the speed. Electrical brake and batteries storage could recover the energy in an electrical framework. The scheme in the slide shows a diesel-electric hybridization. An electric motor generator acts as brake and is able to produce electrical energy that can be stored in batteries and reused in the electrical motor. The energy involved in the ramping sections and braking situations can be regenerated and reused. A regenerative brake is shown in the picture. The system allows recovering the braking energy. It is coupled directly to the transmission system by using a gearbox. The electric motor generators attached to the gearbox allow charging the electrical storage system, typically batteries, or improve the traction power when acting as motor. The evolution of the full electrification of the heavy freight trucks moves both the market of electrical vehicles and the supply of electricity for recharge of the batteries. Accordingly to the nowadays development, the recharging rate for a heavy truck is estimated between 300 and 500 kilometers, and the charging time should be less than 45 minutes, in coincidence with the resting time of the drivers that occurs each 4 hours. The electrical charging rate is in the range of 1 megawatt. The possible simultaneity of demand and the need of certain number of charging points in the area has impact in the grid that should be compensated with electric storage. It means some changes, as the electrical charger network will impact the electrical grid, and the new dispositives for fast charging, including electrical storage. Storage of electrical power becomes a necessary support in both the vehicle, the charging point, and the energy supply system, which is the electrical grid. Storage should be considered also in the connected point. The set of the storage elements includes mechanical, flywheel or compressed air, electrochemical batteries, capacitors, ultracapacitors, magnetic energy, SMEs, or hydrogen production. The compensation and stability of the grid requires of fast and powerful storage systems as SMEs, and also large energy accumulators as pumped hydro, both with lifetime larger than 30 years. Also, sodium-sulfur batteries can play a role. They are high power, able to act in systems with energies between 10 megawatt-hour and 1 gigawatt-hour. The distribution of charging points is growing accordingly to the development of the market demand. Sales of electrical vehicles is also linked to the charging grid development. The central countries have a very dense grid supply points, growing faster than in the countries where the demand of electric vehicles is smaller and the development of electrical mobility started later. The supply of electrical energy has a central element, which is the grid. It operates from a mix of energy suppliers based on fossil fuels, gas, coal, renewables, nuclear plants, etc. It includes non-zero emission sources, as is the case of fossil fuels. The production of electricity achieved 2,641 terawatt-hour. At 30% corresponds to fossil and 60% corresponds to nuclear and renewables. The electrification goes ahead helped by the market impetus and the storage of electrical energy. Among the presence of technologies and development of new devices. Thanks for your attention. Thank you very much.